Luke Lightstein, I am your uncle.
You're my uncle. You're my uncle. No, no. Oh, oh, oh.
Good enough. Oh wow. F9.
Well, Darth Rutherford, I think you got me this time.
I did. I took you out, Luke Lightenstein.
Yes, indeed. I think you are way too, I don't know.
You like my mask?
Ugly.
What?
You are ugly.
I'm part
You
machine.
look like that Darth Maul guy from the story.
He was red. This is a Mexican wrestling mask, man.
I thought it was like you were like.
Oh yeah, it
Darth
is my
Rutherford.
normal Darth Rutherfordness. I forgot. You're right. It is.
Okay. Well, I think we should like learn about.
Probably. I am your uncle.
Oh, not that.
Yeah.
Oh my. Okay. Well.
Oh, this is really uncomfortable.
It
I'm
is
gonna
very
take mine off
kind
too.
of. Yeah, I'm kind of hot here.
Aha!
You know, I think I'm gonna take off my jacket.
Yeah.
Yeah. All right, we're taking it off.
Easy there.
Hey, we
Turbo.
got the peanut gallery back there. Okay, I think we're back to
All right.
regular deals here. All right, ladies and gentlemen. Today we want to learn. Was that stupid or what?
That was
Okay.
great.
It was wonderful. Okay, podcast 7.1. Hey, we're going to learn about. What are we going to learn about today?
Looks like some electromagnetic radiation.
Which is better known as
Light.
Light.
Which is why we had light
sabers. Yeah.
for a fight. Yeah.
For a fight. Yeah, and I fell down and he killed me. That was kind of not very good.
Wasn't
Okay.
it great.
It was great.
Okay.
Okay.
Amazing actors.
We are,
should be stuntmen or something.
That would be good. Yeah.
Yeah.
I
You might be able to pull that off. I don't know.
I don't know if I could do that.
I had
All
a
right.
friend who's a stuntman. He taught math, and he was a stuntman at part-time.
Wow.
Pretty crazy.
I've never known a stuntman.
Back when I lived in California.
Hey, but before, we're talking about light, right? But light's kind of weird.
Yeah.
Because
why are we talking about light in a chemistry class?
Because, well, there's a connection between light and matter.
Oh, yeah.
And so before we can talk about matter, we've got to talk a little bit about atoms.
Yep.
And we're going to start with an interesting question. How many atoms are in an orange?
At least 5.
I think you're right. It's a little more than 5.
Okay.
To get the idea, what you'd have to do is you'd have to take the, well, how many apples? How many atoms are in an orange?
Lots.
A lot. More than 5, you think?
Probably more than 5.
Probably more than 5. Well, in order to see how many atoms are in orange, you have to take the orange and you blow it up to the size of the
Earth?
The Earth. And you know how big the atoms would be?
Size of a normal orange?
The size of a marble.
A marble.
Yeah. So think of the world filled with marbles.
Okay.
That's a lot.
That's a lot of marbles.
That's a lot of marbles.
Especially including the ones I lost.
Yes. You lost a few on your Darth thing. So the marbles, think of those, and that's how many atoms are in an orange.
Wow. That's a lot of atoms.
That's a lot of atoms.
Yeah, that is way more than 5.
That's way more than 5. So that tells you something about atoms. It tells you that atoms are really, really
small.
They're small.
Very tiny.
I mean, like small. I mean, like way small.
How small?
Way small.
Good to know.
And secondly, something even odder about this whole atom, and we probably know this, is that if you took that marble that was in the orange, which is really way small, and you blew that marble up to the size of a football stadium. This is the Cowboys football stadium.
Okay. So the marble being an atom?
Yeah, so now the marble is a football stadium. We blew the marble
so
up.
we have an atom that's the size of a football stadium.
Yes.
Right? Marble. Okay.
And you look inside that atom and you try to find the nucleus.
All right.
You know how big the nucleus would be?
I'm guessing it's going to be the size of a marble.
It's the size of a marble. So right here in the center of the football stadium, right there, would be a
above
marble.
Right above the 50-yard line?
Right above the 50-yard line. Suspended, think of a sphere the size of a football stadium.
Wow.
And it would be the size of a marble. So this little dot right here actually.
And that's where most of the mass is too, isn't it?
Yeah, it's kind of crazy.
Wow.
Yeah. So what's out here?
A whole lot of nothing.
It's nothing. It's empty space.
And some electrons kicking around.
Yeah, there is some electrons, but they would be smaller than the marble
like
by 10,000 times actually.
Speck of confetti or something.
Yeah.
Okay. Cool.
All right. Oh, one more thing we should say. How about the mass of atomic particles?
Oh yeah, that's good to know.
They're kind of tiny.
They are very.
Since they're so tiny, how big are they? Well, the analogy, I should have had a picture, I didn't realize it, is if you take one proton is to 1, it's like a ratio, to 1 gram. Now, what 1 gram would be like the mass of what?
Paperclip.
Sorry, buddy, this is a paperclip.
There's your paperclip.
1 gram. This weighs about 1 gram. Actually, this is a larger paperclip. It's usually the smaller paperclips right here.
Yeah.
Okay. 1 gram is to 1 paperclip as 1 gram is to the mass of the Earth.
Wow.
I know, it's a lot. So that gives you kind of a perspective that, so protons are
Very small.
very, very, very small. Okay, hey, now we're going to move on. So we've learned a little bit, that was kind of a review. I think some of you knew some of those ratios and proportions from last year, and you learned about atoms. So here, we're talking about light, and I know this is what sounds kind of odd, that's the whole lightsaber thing, is that we want to learn about how light is because it connects things to atoms. So light travels as a
wave.
Of a wave.
So like a wave.
So what do you got there, Mr. Stams?
I just got my little slinky.
Oh yeah, and it's like a colored slinky.
Yeah, color slinky.
Colored slinky.
So I'm trying to sort of.
It's like got red, I see, orange, yellow, green, blue, indigo, and violet.
Yeah,
That's like the spectrum of
The
colors.
funny thing, my 3-year-old, when he sees a rainbow that's drawn improperly in a book, he goes, "Those colors are silly. They're not in the right place."
Yeah.
He knows the order. My 3-year-old. He's 3.
Roy G. Bibb.
Yep. He's very
Red,
familiar with
orange,
Roy.
yellow, green, blue, indigo, violet.
Yep. So
All
get it
right.
right. Get them in the right order.
Now we want to talk a little bit about the parts of a wave.
Okay.
Okay, waves have properties.
Yep.
All right, they have wavelength, they have frequency, velocity, and amplitude. And so we're going to just have a blank screen here and draw a wave. Now you may be able to just label a diagram that folks you have in your book.
Packet. Yep.
In your packet. Now first of all, let's label the parts of a wave. The top of a wave is called the
And peak or the crest.
crest, and the bottom of the wave is called the
Valley or a trough.
trough. I like that word, a trough.
Looks like trog.
Yeah. All right.
I love
And
English.
since it is a wave, it is by definition traveling in a direction, and it's got a velocity. And actually, let's give that a symbol. Call that V.
All right.
That makes sense, doesn't it? Now, what do you like to measure about waves? What are the two key things that are measured?
Frequency and wavelength.
All right. So the first thing you can measure here is the length of the wave, and this is called the wave length.
Length of the wave.
Now, it gets a funny symbol, though.
It does.
Scientists-
Lambda.
It is the Greek letter lambda, and that's what it looks like.
It's like a backwards H with a backache.
Yeah, there you go. And so that's the lambda. The other thing that you can measure is the height of the wave, and the height of the wave is called the
Amplitude.
amplitude. Now, you guys have experience with waves. If you've got sound waves.
Yeah. Different
right?
kind of wave.
So, for example, folks, I have my cell phone, and we're playing some music. Now, what happens, what can you adjust when you're listening to
You
music?
can turn the volume up and down.
You can turn the volume up. So if I turn the volume up, I just turned the volume down, didn't I? So what did I just change?
The amplitude of the wave.
So if I can change the amplitude, doesn't change the pitch though, right?
Nope.
Now if you were to change the pitch of the wave, what would that do?
Changing the frequency.
Which would do what from a sound perspective?
Makes it go up or down. Kind of a woo.
Right.
Woo.
So a low frequency wave is like this. You're better at that than I am. And a high frequency wave is like this. That hurt. Okay.
Kind of funny too.
Yeah, it did. So that's how. But if you change the amplitude, you just turn the volume up, so to speak.
Yeah.
Now in light, what you're doing, if you amp up the amplitude, amp
it up.
There you go. It will make it brighter.
Yeah. Change the intensity of it.
But if you change the wavelength or the frequency of light, what does that do?
Then you're changing the color.
Yeah. So wavelength, lambda, is actually the color. So it's actually a number. It's how long the wave is tells you what color the wave is,
Right.
so to speak.
And in the visible spectrum, we're dealing in nanometers. Usually, roughly 500. Actually, less than that.
Oh, and one other thing we should say
500.
about the velocity here is that light has a specific velocity, and it's 3.0 times 10 to the 8th meters per second.
That is called it's the light velocity. The light's velocity, right?
Yeah.
So it's the speed that the light
speed.
is traveling.
So we
that's
call the speed of light.
Light.
So this is called the speed. The speed of light.
What was that?
I don't know.
It's kind of like Marvin the Martian on the old Looney Tunes.
Now, scientists use the speed of light, and they give a particular symbol for it, and it's c. So it's like a famous number. When scientists have famous numbers, they get like their own letter, and this gets its own letter. C for the speed of light. Don't get that confused though, like with C for specific heat. Same thing.
Or like centi.
Or centi. But this is just, so if you see this equation, most likely it means, like in this famous equation, E equals mc squared. That's the speed of light, and you square it. That makes it, by the way, this is a huge number, guys. 3.0 times 10 to the 8th meters per second. Way big number.
Yeah.
Oh my gosh, ginormous, yeah. Now, what you can do is, we didn't talk about frequency, did we? What's the frequency, Mr. Sams? We haven't talked about
frequency is how fast the wave is moving past a particular point.
And the units that are on that are called the waves per second.
Right.
So if you're standing, so to speak, by a wave and you count how many waves go by you per second, that's called the frequency.
Yep.
It's also called, the abbreviation, a hertz.
Yeah.
Now, where have you heard hertz before?
When someone gives you a Hertz donut. You ever had a Hertz donut?
No.
Hertz donut.
Ouch!
Ah ha ha.
That hurt.
Donut.
No. I was like a Hertz cars or something like that.
Oh,
No.
okay.
No, a hertz. Well, hertz is the abbreviation for, and you've heard like gigahertz for your like radio station. You know, it's a so-called megahertz. That's measuring how many waves per second. Because interestingly enough, radio waves are like light, and so sound travels on the radio waves, your TV waves, or heck, on my cell phone, it works that way. So it's pretty cool on waves. So, and the symbol for, actually we should talk about what is, and the symbol for frequency is a funny V.
It's a nu.
It's actually the Greek letter nu.
So it's not the straight armed V like velocity, it's the squiggly V nu.
Yeah, it's easy to get these mixed up. V versus nu.
Be careful.
Be careful. So here's the equation. If you take the wavelength and you multiply it by the frequency, it equals the speed of light.
There it is. And the speed of light is constant. It doesn't change. And so
Yeah.
if you make one go up, the other one goes down.
Yep. Now, this is what's called the electromagnetic spectrum. Magnetic spectrum.
Yeah. Notice that the visible spectrum is a very, very, very narrow band in the full spectrum. It's only a small region. Now, think about it. Our eyes are only sensitive to that very small range. And that's probably a good thing because if they weren't, with the amount of radio waves and television waves and microwaves and stuff coming, cosmic waves coming from outer space, there'd be a lot of, if you will, light noise coming into our eyeballs. So it's probably good that we can only detect a small amount.
Yeah, it's kind of odd that human beings can only detect such a very small band of light, but really there is much more, if you will, light. We don't use that term scientifically, than exists. And there are, right here, gamma rays, X-rays, ultraviolet. That stuff will give you sunburns.
And some insects can actually detect ultraviolet, and some other animals, like a snake, can detect ultraviolet.
So if you were an insect and you could see in the ultraviolet spectrum, what color would you see?
Super purple. I don't know.
That's the interesting question. Is it's like another color that we have no comprehension of.
Exactly.
It's like talking to someone who's colorblind and trying to explain like red to them, or talking to somebody who's blind and trying to explain color to them.
Right.
It's just they can't understand.
Exactly.
And so, so there's lots more light, if you will, quote unquote, than you can see. Another thing that's important to understand about this is it says increasing frequency. Now, I'll bet you could figure this out. But what happens energetically as you go in this graph from the right to the left?
Energy.
Which would you rather have hit you? A radio wave, an AM, an ultraviolet,
I'm going to want
X-ray?
the radio wave to hit me.
Why is that?
Because it has way lower energy than, say, like a gamma ray.
So these have high energy up here.
Yep.
So I want you to write that high energy on this side. And this side right here is low energy.
Yeah.
This is why, folks, you probably all have had an X-ray. And of course, when you have an X-ray, take pictures of your bones or whatever inside your body.
They cover you in lead.
Because they don't want you to be overexposed.
Exactly. They only want just the area.
Why would they? What would happen if you were overexposed to X-rays?
Well, it can damage your DNA, and things can start to mutate. You could get cancer as a result, or pass mutated, or turn into the Incredible Hulk if you get zapped with gamma rays.
Actually, that's not true. It just would cause deformations and could kill you.
Actually, says you.
Yeah, actually,
I can get superpowers.
You going to get superpowers? You had them.
Exactly.
Actually, let me tell you a story, a little more serious story. I found this out talking to my mother. My grandfather was a medical doctor back in, he got his medical license in 1918, 1920, something like that, so a long, long time ago. And they invented this thing called a fluoroscope. You know what a fluoroscope is, Mr. Sam?
No, actually, I don't think
Basically, it's an X-ray machine where they could take like real lifetime images of the person.
Oh, wow.
And so what my grandfather would do is that, let's say Mr. Sams had broken his arm.
Okay.
And so he comes to me.
In a lightsaber fight.
Okay. All right, so, and they would take this tabletop X-ray machine, and he would set your bones by looking down.
Oh,
through them.
wow.
This is before, of course, they knew things about X-ray machines. So actually, it was a bad thing. My grandfather got lung cancer. He'd never smoked in his life, and actually, he went to his doctor as a doctor, and they said, Dr. Casebolt, we're going to have to cut your hands off. And
Wow.
he said, I'm a surgeon. You're not cutting my hands off. So he died of lung cancer with never smoking a cigarette in his life.
Wow.
So, yeah, kind of a sad story, but
Yeah.
nobody knew back then. So X-rays for lots of time, not good. Anyways, interesting story.
Wow.
Yeah.
Very.
Okay. Now, let's talk about light some more. Okay, let me turn the color change here. All right. How does matter behave? It acts like a
Particle?
particle. Hey,
Hmm.
did I not change the color?
I don't know.
I see white color. I went to white. A particle. What does that mean?
Like a point in space.
Like a tiny, tiny little ball.
Yeah.
Particle. So matter. So we're talking about matter now, not light. And we'll connect these in just a minute. All right. So light is a particle. So if I throw a ball, let's say I'm playing pool or something like that, and it were to hit the table. This is a pool ball or a billiards ball or what do we call it?
Yep.
And it would come off. As it turns out, exactly the same angle. So whatever this angle is, this would come out at that same angle. So that's how that's how matter works. Okay. But then this guy named Max Planck shows up, and you can see when he was alive, and he began to look at matter.
Mm-hmm.
And he said the amount of energy is actually, here's a fancy word, quantized. T-I-Z-E. Quantized dyes. There you go.
Yeah,
it is
quantized.
quantized.
Yeah.
What does that mean?
That means that energy can only be in specific amounts. It's not like a continuous range that it can be in. It can only occur in a specific quantity, and we call those small quantities called a quanta, or quantum if you have one. Quanta is plural.
So they come in these tiny little packets of energy, and you'll see how this works. This is really kind of a confusing thing to understand.
Yeah.
All right, so now let's go back to light. Let's talk about light for a minute.
So matter
Light
behaves like a particle, and then he said
light travels as a
wave,
but
also
as
as
a
a particle. We
This
call
is-
that wave-particle duality.
Yeah.
Yep.
I didn't write that down. Yeah. It is the wave particle duality.
Yes.
So is light a wave or a particle?
Yes.
Wait a second. Is light a wave or a particle?
Uh-huh.
Who's on first?
Yep. I don't know.
Okay.
Third base.
Okay. A particle of light then is called a
Photon.
photon. All right.
Now we're entering into Star Trek land here, folks.
So, folks, a particle of light is called a photon. So light actually is a particle, but it also travels as a wave. And we'll illustrate that with a picture in just a minute. Now, does light have mass?
No.
There's actually an interesting quote in one of our textbooks. It says light does have a teeny tiny. It makes actually our, remember how the paper clip to the earth makes that look heavy. Thing.
Yeah.
So maybe so.
Yeah.
Okay. So you can kind of see this. So here's a picture, a good picture that light is both a wave and a particle. So it's not. I think the way that's helped me to understand this, I like to think of the particle moving along the wave, but that's really not very accurate. It's not perfectly true. The reality, it is the wave, and it is the particle.
Right.
And that is just kind of conceptually hard to get your brains around.
You have to think of light as kind of existing in the fourth dimension, if you will,
Yeah.
but we exist in three, and so we can't quite wrap our heads around it. It's just, okay, here you go. Picture a four-dimensional cube.
Okay, hold on. Let me draw a cube. All right. I got a cube.
Right.
I can draw a picture of a cube.
Now what you just drew is a three-dimensional representation.
It's got length, it's got width, and it's got height.
Yeah, no, I'm
good.
sorry. That's a two-dimensional representation of a three-dimensional object, which you just drew right there.
All right, because they're looking at two dimensions.
So now, if you can think of, right, now if I lived in two dimensions and someone said cube, I would have to go, well, I know it has it's kind of like a square, but it's kind of like a bunch of squares together. But if I live on two dimensions, I can't actually visualize that because I've never seen anything like that. So when I say that light has properties of a wave and it has properties of a particle, but it is both at the same time, you can't really get your head around that because you don't really experience that in your three-dimensional world.
So it is kind of hard to understand that the world is bigger,
Yeah.
more dimensional than we think.
Yes.
Yeah, this is kind of particle physics stuff. It gets
Yeah,
kind of crazy.
good times.
All right, and actually, this is a pretty cool picture here that just,
What is
this
that?
is the photon traveling on a wave.
Oh.
I got it on the internet. It's pretty cool. Okay, and I thought this was pretty cool. This is Erwin Schrödinger. We'll talk about him later. And, of course, the particle says to the wave, "No one told me that I was going to have to work with her." Ta-dum, boom. Okay, now what we want to do is figure out how looking at light helps us to understand waves.
Right. This is back to chemistry now.
All right, yeah. And it all started with some scientists analyzing the spectrum of hydrogen gas.
Yes.
Now, the way they did this, well, tell you what, we are going to jump to an experiment right now, and we're going to show you what it looks like. You've probably seen this before. We won't probably do the whole thing because it's too hard, but
Yeah.
you'll
We'll do
get
a bunch
the idea.
more in class.
Yeah.
So, folks, here I am looking at, I've got a spectral tube right here. So I'm going to apply a whole bunch of electricity. This could be like 10,000 volts or something like that. Do not put fingers in sockets when you turn on.
Duh.
That's one of those duh moments. And in this tube, let me pull this out here, I have argon gas. So this is a tube filled with argon gas. I'm going to turn it on, and it's going to make a light. It's like basically a light bulb. You've probably seen neon lights. And so as I turn it on, it makes a really cool purple color. All right. Now, the thing that's kind of cool that you can do is that you can take your cool glasses that I was wearing for our lightsaber fight, and these cool glasses then break up the light into a spectrum of colors. Okay? And so we'll see if we can do that with our, does that make us do
It does.
And so does it split it apart?
Uh-huh.
Oh, how cool is that? So you can see as you're looking. What do you see, Mr. Sam?
I see a bunch of different colors. I got a purple line and green line and maybe like a red line and possibly some yellow in there.
Okay.
But we can see distinct colors that are not in the original color of the light. We have the colors all split up.
Okay. Now, let's now do that, and let's take a shot.
Oh, nice.
Woo! Okay, that was no fun. All right, and I have another spectral tube, and you've seen these before. This one's filled with xenon gas. And so I expect to see something different. You'll see lines like we just did a minute ago, but you should see different lines because it is a different element. We'll talk about that in a minute too. All right.
Ooh, okay.
Blue color.
Nice blue color this time. I put on my glasses.
So Mr. Sam's is putting the glasses on the...
Yeah, it's not quite as good as the last one. We get a little light coming in through our door there, but I've got a blue line, looks like a little bit of yellow, maybe a little bit of red. These are not quite as distinct as the last one.
Yeah, I probably have too dim of a bulb. But I think you get the idea that every element has its own set of spectral lines. And actually the more interesting thing is not the lines that are there, but the lines that are not there. Why don't we see all Roy G. Biv?
Ah.
Why don't we see those?
We'll talk about that.
And we'll talk about that. All right.
So this picture that we have on the screen now is the atomic spectrum of hydrogen. We didn't do the hydrogen spectrum at all when we did this, or on just a minute ago when we did the experiment, but we can see it right here, what it would look like. And this is interesting. So you would just see four lights, red, kind of teal, if you will, and a couple of shades of purple. Now these, if you recall, have wavelengths, and they have particular numbers associated with them. I don't know what they are off the top of my head, but this would be probably in the 420 nanometer range in nanometers. Nanometer, by the way, how big is a nanometer?
Tiny, 10 to the 9th meters, negative 9th meters.
So it's
Sorry.
1/1 of a meter. So 470 or 20 billionths of a meter, and this purple would be somewhere in the 700 nanometer range. The reason I know that is that the visible spectrum is somewhere between roughly 400 and 700 nanometers. Did I do this
I
wrong?
think they look backwards. Mr.
I've got them
Beckman.
backward. Yeah,
Yep.
this is the 400 side, and this is the 700 side, isn't
Yep.
it? Yeah, my mistake.
Yeah, because the red is low energy, and low
Yeah,
energies
I
have
did it wrong.
long wavelengths. That's how I
So
remember
this
that.
would be, 420,
Yeah.
and this would be like 680 or
That's more
something
like
like that. Yeah, okay. And so here's another schematic picture
Right,
of
and
this.
this is going to kind of tell us why we have distinct lines, like Mr. Bergman was saying when he did his little demo there, versus the continuous Roy G. Biv spectrum.
So what Mr. Bohr, who figured this stuff out, he looked at these lines of the hydrogen atom, just like we can see here, and he found this particular wavelength, and he said, if you think of this as a little ball, if a ball falls from this level, there's 4 levels. You can see the first level they call the ground state, level 2, level 3, level 4. Think of this like a building. It's kind of funny because it's got a very tall first story and the second story shorter, etc. But if a ball fell from level 3 to level 2, that would be this red color of light. And if it fell from 4 to 2, it would be this teal color of light.
It's falling further, so therefore it releases more energy.
And etc. We go here and we get different colors of light. Now, here's the odd thing about this. If you were to think of light as a particle, then it's easy to envision it falling. So if I were to drop this heavy object onto the table.
Okay.
Actually, you can't see the table, can you? All right.
That's right.
Onto my hand. I'll try and catch it. I can drop it and it releases a certain amount of energy. Ouch! But if I were to raise it a little higher out of the screen, I would drop it. Ha! It hurts even more, right?
Right, more energy.
Because it gives more energy.
Further.
Now that makes sense, but here's the problem about this. The energy can either be, let's say this is level 1 where my hand is,
Yeah.
and this is level 2.
So the electron can either be here or it can be here, but it can't be anywhere in between. So
You mean it can't, wait a second, if I drop something
No, it's not.
and it falls
It's
from
not
here
falling.
to here,
It's not falling.
it will have to be in between here and here, right?
Right, but the electrons don't actually fall
Why?
because they can't be in between. They can only be here or they can be
But
here.
how does it get from here to there?
I'm not a particle physicist. I don't know. It just does. It just goes. It goes from here and then it goes there.
And actually, I have a way to explain this, which we'll get to in a little bit later. I think it's in the second podcast, but it has to do with the fact that it kind of changes the shape of its movement. It has to do with atomic orbitals. There's s orbitals and p orbitals, and you might remember that from last year. So that's still not really true. It has to do with the fact that it's a particle and a wave, and it's something that's, again, one of those hard to comprehend things. It can't exist in between.
No, it's
here
like
and
there, and then it's not there, and then it's back where it can
Yeah.
be again.
And here's another picture. Actually, our pen marker. Here's another picture that we can take a look at it. And this what we were just looking at. It was called the Balmer series for hydrogen, and these are the different fallings. You know, here's from level 4 to level 2, and here's 3 to 2, and they give off particular. Here's the actual numbers of those wavelengths: 410, 434, 486, 656, and then for the infrared spectrum, if they fall down to the first level, we get something called the Lyman series, and there's even one called the Paschen series.
Yep.
Okay. All right. Now, one thing that we saw on the podcast or on the demonstration just a bit ago is we saw several different elements, right?
Yeah.
One thing that's cool about this, if you have a different element, this of course is sodium right here, and this next one is mercury. They have different lines.
They do.
And how can that help a scientist?
Well, if we had an unknown substance and we could make a little gas tube out of it like we
Yeah.
had there and run some electricity through it and find out its spectrum, we could identify what element that is or what substance we're dealing with.
And of course, scientists also use this to look at the sun.
The sun.
Or the stars, not just the sun, of
The
course.
stars.
Because has anybody ever been to the sun and scooped a piece out, brought it back to the earth, and done a chemical analysis?
Not that I'm aware of.
I think you have a problem because it's
Yeah.
6,000 degrees Celsius or millions or whatever. It's
it
really
is.
hot.
It's hot.
Way hot. You'd burn up and boil,
Mhm.
and that'd be bad. So how do they know that? They say, scientists, as far as I know, they always say, the sun is made up of 98% hydrogen or something like that.
Yeah.
Why? How do they know that?
They look at its spectrum.
Yeah, they just looked at the light, and so they can then point their spectroscopes, those fancy spectroscopes, and
Yep.
they can say, oh, that one's made of hydrogen.
Yeah.
And you look at the other one, you say, that one's made of hydrogen.
Yeah.
And the other one over there, yeah, I see more hydrogen. Lots of hydrogen in the air in the universe. Okay. All right. This leads us to the Bohr model. So Mr. Bohr sat down. He did some
Math.
math.
'Cause
Ooh,
that's what we should all be doing in our spare time.
math. He was like Joe mathematician, and he came up with an amazing equation.
Yeah.
It is the Bohr equation,
Yep.
for lack of a better term.
There it is.
And he says the energy of a falling, if you will, is equal to this number, a very
A
small
falling
number,
electron.
a falling electron, pardon me, which doesn't
Falling
doesn't exactly fall.
Right.
Yeah, it's just this appear disappear thing, and it's equal to z squared over n squared. Now, what's z? It's of course the atomic number
Yep.
of the atom. So for hydrogen, the atomic number would be 1.
1.
And n is the level in the electron. Remember, we
Right.
learned just level 1, we have level 2, we have level 3. So you take that number and you square it.
Right.
Okay.
Just as a side note, he only did his research on the hydrogen atom, and this equation really only works nicely with hydrogen because there's all those other electrons in all the other atoms and all the other nuclear interactions going on. It works with hydrogen.
That's
That's
right.
about it.
Well, yeah. Now, here what we're going to do is So what we want to do is we want to try and figure out the energy or the wavelength of an atom that falls from level 2 to level 1. Wait a second. Electron level n equals 1 to n equals level 2. Or the energy level required.
Yeah,
so
it's endothermic. It's going in.
I like to do E1 and E2.
Okay.
Now E1, if you go back, I always forget this number, is negative 2.178. Actually, you don't really need the negative sign because you're going to make a change. You'll see.
Yeah.
Times 10 to the minus 18th. Now this works with hydrogen, so the Z is 1, so that's 1 squared over... Now this 1 here represents n
energy
equal
level.
to 1, so
Yep.
that'll be 1 squared. So I don't even need a calculator.
No.
2.178
I don't even need a
times
calculator.
10 to the minus 18th, and that's joules.
And I need a calculator.
This second one, you're going to say equal to 2.178 times 10 to the minus 18th times 1 squared, still hydrogen, over now 2 squared because now we're at level 2. So basically you'll divide that number by 4, and that is what, Mr. Sims?
5.445 times 10 to the negative 19.
Now what you're really trying to find is the change, or the delta E, which means I'm going to take this first number and subtract this second number, and what do you get when you subtract the two?
1.6335 times 10 to the negative 18.
And that is the energy of the electron falling, or actually no, we're actually going the other direction, from n equal to 1, when he then reappears at the higher energy level of n equal to 2. And the question is, how much energy do you need to add to him to get him to bump up to the next level?
Yes.
And that's the
how
energy.
much.
Now,
And
I think the question
asks
asks
for the wavelength.
for the wavelength. Now, here's some equations we need to make sure we know. And I don't think we've written these down yet.
We gave you one earlier. We gave
Well,
you
let's write them all down right
lambda
here.
nu equals C.
E equals H
nu.
times nu, and that's the frequency,
Mm-hmm.
right? And nu is equal. Oops, nu is equal to C over lambda.
Mm-hmm.
Or this is a redone of, we said lambda nu equals C.
Right.
Now if I plug in this right here, I can also say E is equal to HC over lambda. Now there's a letter there, we don't know what it is. What is H?
Planck's constant. Remember Max Planck?
Mr. Max
This is Planck's constant.
It is 6.626
Yep.
times 10 to the minus 34 joules seconds.
Yep.
That's a small number.
That's a very small number.
That's an itty-bitty number.
But
So,
the speed of light is a big number.
well, we know the energy. Guess what? So
We
what's
do.
that? That's equal to E.
Mm-hmm.
So if I want to find the wavelength,
Plug and jug, do a little
I'm
algebra.
going to use this equation right here. So I'm going to say E is equal to HC over lambda.
Mm-hmm.
Now if I solve for
Lambda.
lambda, I can cross multiply, right? So I can say E lambda equals HC.
Mm-hmm.
Or if I want to get lambda by itself, he would be HC over E.
There it is. Plug and jug.
So that'll be 6.626 times 10 to the minus 34th times the speed of light, which is 3.0 times 10 to the 8th, divided by my energy, which was 1.63 times 10 to the minus 18th. And I get
1.22 times 10 to the negative 7.
And that unit would be, I didn't use my units here.
The wavelength is measured in meters.
So that would be meters. Now while we're at that, oftentimes we like to, I don't know if I have a blank screen yet. No, I don't. Let me use the bottom of this. If I have, what was it,
1.22 times 10 to the negative 7
1.22 times 10 to the negative 7th
meters. Often we'll see this in nanometers.
1 meter is equal to 1 times 10 to the 9th, or billion nanometers. And I don't need a calculator on that. That becomes a 122 nanometers. Okay, you just multiply, move the decimal over 9 places. And since this was 10 to the minus 7th, then trust me, it's that. Okay. So this cool equation that we just did, which you may not think is so cool, but this cool equation, Mr. Bohr was so excited. It predicted everything about the hydrogen atom, and everybody was, arms about how wonderful it was. However,
didn't you win a Nobel Prize for that?
I believe so. But guess what?
It only works.
It only works for the hydrogen.
Yeah.
Because you see, what happens is what happens when this equation becomes, when Z becomes 2. Well, then you say, well, it's just 4. 2 squared is 4. It'd be right. It'd be easy, right?
Yeah, sure.
But the problem with the hydrogen atom is this. Or the problem with non-hydrogen atoms. Of course, atoms have a central dense nucleus.
Mm-hmm.
So let's just take a helium atom, the second most simple element there is.
Yeah.
2, 4. He has
4,
4, 2. Whatever, yeah. 4 and 2. He's got 2 protons, and he's got 2 electrons.
And 2 neutrons, by the way, in the middle.
Yeah. So if you were to think of it, you get the central dense nucleus, and you get an electron here and an electron here, way out here. This is an atom. What he had not accounted for, what happens if you have an electron and it gets near like another electron?
They repel each other.
You see, and that's the problem. You see, when you had a nucleus, one proton and 1 electron, the only thing you had was attraction between the proton and the electron. That's the hydrogen atom. But when you have the 2 electrons, you now have repulsive forces that push these guys apart. And that messed everything up. So it doesn't work. And that's just with helium. If you take like uranium with 92 protons and 92 electrons,
whole another ball of
it's
wax.
all screwed up. Okay. All right. So that gives us a quick introduction to podcast 7.1. And so what we want to do is just give you an idea. Next time we're going to talk about things called quantum mechanics. Oh yes, my goggles. You took my goggles.
Quantum mechanics.
Oh yes.
So then we can learn how to do quantum leaps.
Yes. We can leap into the next dimension.
Yes, with our lightsabers.
And I could become Luke Einstein.
And then maybe
whatever
you'll
his name
be
is.
like my uncle and I won't, or I don't know.
You're way too young to be my uncle.
I know.
I think I need to be the uncle because I'm older than you.
Yeah.
By like a lot.
Yeah. Oh well.
Oh well. We will catch
I wanted
you.
to wear the mask.
I wanted to wear the cool glasses because I can
Yeah.
see psychedelic colors. He doesn't get to see that.
Whoa.